Entropy is a state function, much like enthalpy. That means that in order to figure out the change in entropy, all we need to do is worry about the final state, so final entropy of a process, and the initial entropy of a process. It also turns out that the change in entropy can be calculated by dividing the heat of a process over the temperature at which the process takes place. The important thing to note, though, is that the process has to be reversible. Now, at this stage, you might yell out, but hold on, did you not tell us that there is no such thing as a truly reversible process? True. That is absolutely true. There is no such thing as a truly reversible process. But in this particular situation, we are talking about an ideal case. We are saying, well, what if a process was in fact truly reversible? Then we could apply this equation. You may say now, well, hold on, how could we do that? How could we make this assumption? Well, we can, and we've done it before. Remember this? PV equals nRT. What is it called? It's called the ideal gas law. So we know that this is not how gases truly will behave, this is how an ideal gas would behave. And it turns out that even though we know it's not absolutely correct, when we use this equation to calculate pressure or volume, it comes really close to the real thing. So it's close enough for quite a lot of calculations and quite a lot of predictions. In fact, it's damn close enough. And the same thing applies to this equation. Now you may say, okay, fantastic. What can I do with it? Well, recall that heat of a process is the same as the enthalpy process at constant pressure. At constant pressure. This means that now we can say the change in entropy, delta S, equals the enthalpy of the system over the temperature at which this process is happening. And now you might also say, well, big whoop. True. However, this allows us to calculate a whole number of things. And I'm going to show you a few examples. Well, actually, really just one example. We're going to talk about calculating the entropy of a phase change. So we're going to go from solid water to liquid water, and we're going to figure out or calculate the delta S. And then we're going to do the same thing for liquid water to gaseous water. A couple of things we need to know before we start. For argument's sake, we're going to say that we have 2 moles of water. And now we are ready to go. So our equation from up above is delta S equals change in enthalpy for the process over the temperature at which the process takes place. So let's think about it. For the melting of ice, okay, the ice starts to melt at 0 degrees. So that is our temperature of the process. And remember, when we're doing these calculations, we need to use the Kelvin scale. So the temperature, if the temperature is 0 degrees Celsius, it means it's 273 Kelvin. Okay, so we have our T. What about our enthalpy? Well, we are looking for the enthalpy of the process of melting. And that is also known as the heat of fusion. And the heat of fusion for water is 6.01 times 10 to the third joules per mole. Okay, now we're ready to go. So we have the enthalpy of our process, the melting of ice into water, the melting of ice to become water, and that is our heat of fusion. So we can use that value. So it's 6.01 times 10 to the third joules per mole. And I have said that we have 2 moles of water to begin with. And the temperature at which all of this occurs is 273 Kelvin. So a couple of things. This mole and this mole will cancel. So 6.01 times 2, 12 let's use the right color, make it consistent. Nice purple. So 12.02 times 10 to the power of 3 joules, because we cancel the moles, over 273 Kelvin. And that gives us 44 joules per Kelvin. So the entropy of fusion of 2 moles of ice is 44 joules per Kelvin. Hold on, that doesn't sound right to me. Let me just check that. Oh no, it's all good. Okay, let's move on. So now we're going to calculate the entropy that is related to conversion of this liquid water into gaseous water. So we're using the same equation. Delta S, so the entropy of the process we are interested, is equal to the enthalpy. See, I make a mistake there. The enthalpy of the process we are interested in at the temperature at which the process takes place. Well, what is the temperature at which water turns from liquid into gas? It's 100 degrees Celsius. And 100 degrees Celsius is same as 373 Kelvin. Now we need the heat the enthalpy that is associated with vaporization. And funnily enough, that is called the enthalpy of vaporization. I'm just going to shorten that to VAP. And that equals 4.066 joules, 4.06 times 10 to the power of 4 joules per mole. Okay, now we're ready. So, once again, we have 4.066 times 10 to the power of 4 joules per mole. So that is the heat of vaporization, multiplied by the number of moles we have in our process, and I said that we have 2 moles of water at the start, divided by the temperature at which the process takes place, which is 373 Kelvin. Okay, so 4.066 times 2 should be 8.132 times 10 to the power of 4 joules. Remember, the moles cancel. Over 373 Kelvin. And if we plug that in, we should get 298 joules per Kelvin. And let me just quickly check that. So this is same as 81,320 divided by 373. Oh, I made a mistake. So it's not 298, it's 218. Make sure it's orange. So 218 joules per Kelvin. So using the enthalpy of a process and the temperature at which a process takes place, we can calculate the entropy of a process.